Sudoku rules apply. Entropic lines, each of these are individual entropic lines. That's reasonable. All of those are entropic lines, and they differentiate that way. And then here comes the weird friggin' rule, which is each circle is the fulcrum of a balance whose balance arm is a straight line passing through it. So, like this. Balance calculations are made using torque. A weight 3 cells away from fulcrum contributes thrice the torque of the same weight hanging 1 cell of the fulcrum. So here, this is 2 cells away, which means this, since this is equal, this must be double that. Same thing here. This must be double that, because that's 1 cell away, 2 cells away. So these cells must be double that, and this cell must be double that. So this is a multiple, which we'll get to in a second. If the line that passes through the fulcrum is horizontal, then the sides are balanced, equal torque. If not, the lower side has a larger torque. So this weighs more than the sum of these. Lines are massless and do not affect the torque calculation. That's the puzzle. I'm going to see if I can figure it out. First thing I notice is that if this is n, this must be 2n. Must be relatively low, considering that this, double of this, so this is essentially 3n. Double that, so 6n makes this. So whatever n is here, it must be 6 times whatever this is. The only way that can be possible if that's a 1, and if these sum to 6. Or, well, if those are 6n. So this is double that. These must come to 3, which must be a 1 and a 2. That's 2, that's a 1. That's not too bad. Are the squares also... Yeah, I think that since it goes into this, this also is an entropic line. So 1, This must also be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Can't be a 1, can't be a 2, must be a 3. Can't be a 3, can't be a 1, must be a 2. Can't be a 2. Could be something else. Which means grand total, this accounts for 1 weight, or wait a second, no, it accounts for torque. So it's the sum. Yeah. So it doesn't matter what the torque is here. This is just the total weight. 1. So this weighs 1, 2, 3, 4. And this has 4 weight upon it. So this must equal essentially a weight of 4 here. Regardless of everything else, that just weighs 4. There's torque that we can figure from balance, but this is the torque of 4. This is triple that here. This, whatever this is, must be larger than some of these. It can't be a 1, could have a 2, could have a 3. So it could be 5, which means this is the minimum of 6. Can't be 8. It could be 6, and that could be 2, 3. And then that would carry over. But this is going to be a nice, hefty weight, because this is at least bigger than that. So we've got a minimum of 11, and it's on a torque of 3, so it's going to be like 33 something weight here. This is its own thing as well, so the sum of these is bigger than the sum of those, but natural. This is the same parity as this, has the same entropic line, but this weighs more than that. So it must be... Whoops. If it's a 1, 2, or 3, it must be a 2 or a 3. If it's a 4, 5, or 6, it must be 5 or 6. If it's a 6, 7, 8, it must be 7 or 8 or 9. Here we have the same thing. 1, 2, 3. It can't be a 1, 2, 3, since this can't be a 2, 3. This could be a 4, 5, or a 7, 8. Cool. We just know that those are different as well. Yeah, and that these have the same entropic linedness. I don't know much else about these lines, though. Because this isn't necessarily true that with this must continue altogether. Because it could be big, medium, small, medium, big. It doesn't have to be the same because it is a different line entirely. Likewise, this is also a different line entirely. It's interesting how this contributes like 3 times the torque. This contributes 4 times, and that's all that it does here. Do I have to calculate what the possible torque is for this? Like, what's the minimum torque for that? This is 6. This could be, yes, this could be 11, which would be 33. 33 plus 4 would be 37. This is a minimum weight of torque of 37. And here we have double this. What's the biggest that this could be? 17, 34. Okay, so we can already surpass. We could also go under. This was the minimum here. What if it's the maximum there? 9 and 8 would be 17. 17 by 3 would be 51. 51 plus 4 is 55 over on the left here. At a minimum here, we have 9, 18 plus 6, 24, 28 is the minimum we're looking. Oh no, 28, 29. Yeah, 28. 28 is the minimum that we're looking at here. Okay, so we have a bit of range to work with. So this is already solved in terms of fulcrum. That's solved in terms of fulcrum. This is interesting though, because actually this could be the same digit as that, and it just comes down to those two being different. I don't quite have enough information for that. So it can't be a 1, you know. Can't be a 1 or a 3. Could be a 2. Yeah, we had no information about that specific cell. This can never be a 5. Because if that's a 5, this would have to be bigger than that, which would have to be a 6, which it can't be. Is there a world where this is 8, 9? So what's the maximum of this? We said it was 9 plus 8 is 17, which is 51, 55 total. What's 3 times 17? That cancels that out. Then 4 times, yeah, this can never be 8, 9. Because if this was 8, 9, then, oh, this weighs twice, so this is only 2 across. That's 55. That's 17 times 2, which is 34. Oh, so it could be, couldn't it? 34 plus 6, 40, 44. With that, it could be 44. Darn. Wait a second. Why is that a 2? That doesn't make sense. What the heck? What did I do? Oh, did I... Sorry, this is meant to be 6. Whoopsie doodles. I did a big oopsie. Let me just completely fix everything I just did. That's a 2. That still has to be a 1 anyways. No, it doesn't have to be. Any of those could be a 1. That can't be a 2. Okay. Oopsie doodles. 6 has to be somewhere here. This can't be a 6. So that means that it has to be 7, 8, 9. Can't be an 8. 7, 8, 9. 7, 8, 9. 7, 8, 9. That's all that continues. Yeah, whichever the intersection is, that specific cell radiates upwards. So this cell and this cell have to have the same weight to them, which is kind of interesting, honestly. So this has a different parity than these. These are also different parities. This is a minimum of 5. This has to be in the upper. Yeah, because if any of these are in the upper, then it would lose. These, yeah, so this, breaks. Breaks. This has to be in the upper register. It can't be an 8, which means yeah, so this has to be a one of them is 1, 2, 3. The other one is 4, 5, 6. Well, obviously neither of them can be 6. If this is 9, then these have to be 4, 5, which they can't be, which makes that a 7. Which means these can't be a 1. That can't be a 3. But we know that I guess I can't actually. Sorry, what am I doing? These aren't equality. This just has to weigh more than that. So this could absolutely be a 9. This could be a 1 and a 4 pair or something like that. Yeah, that's fine. I mean, this still can't be a 3. This has a minimum weight of now 5. Well, this can't be a 1. Minimum weight of 5. Minimum weight of 7. This is minimum weight of 12. 36 plus 9 is 45. This is a minimum weight of 45 over here. Interesting. So, interesting observation. This is a high digit. That means this is not a high digit. That's the only... So this and this have to be the exact same. And they're not high digits. Have to be in the same range. And they're not high digits. That can't be 1, 2, 3. If these were high digits... Oh, wait a second. No, sorry. They could be high digits. Because this is not a high digit. Okay, never mind. My observation is stupid. This could still be 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. Because obviously that can't be 6, which means this can't... Well, and this way it's more, so it can't be 6 or 9. Whoops. Whoops. There we go. Also, since this way is left, this can't be a 4. Also, since this way is left, it can't be a 7. Those are the options that I have. This also, then, because there's no 6 here, can't be a 5. Okay, so the logic still continues. I just needed to fix that jiggery. We don't know what those could be. We know that those are the same parity. Could this be a 4, 5? They could be a 4, 5, couldn't it? All of these see 6. So none of these are 6. Somewhat obviously, I guess. This one sees 3 and 1. Which means if this was a low number, then this would need to be 2. That could, in theory, be 3, actually, even though it weighs less. Because this could weigh 2 more than that. It could be like 9 and 7. Remember, this is here. So that's the same parity. Those two all have the same parity. That has the same parity. That has the same parity. We can only ever connect up these if they land on the exact same line. Whatever this is. All of that is. Can I make any interesting deductions from that? I can't see anything. So the fact that 2 has to go somewhere here, which, I mean, isn't crazy. So does, like, the 1, 2, and 3 all have to go there. Or 1, 2, or 3 have to go there. I guess that means that is the middle. That is the small value. So we have 2, 4, 5, 6 is all of our middle numbers there, I guess. This can't be 8. So you have 7, 9 solved. I could actually just do red, 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 red. And there we go. And then we know that this is blue, blue, blue. We don't know whether blue is low or high, though. It could be low or it could be high, depending on what the result of that tile is. Or this tile, because if that's low, then we know that can't be low. Or vice versa. Is there a world in which this is high? What was the upper bound that I calculated for before? If on the left we have the highest possible value, it'd be 9 plus... Well, we know that it... Oh yeah, it could be 8. 9 plus 8. So it's 17 times 3. So it's 51 plus 9 is the left here. So plus 9, 60, because it's 6, 2, 1. That weighs 9 extra on top of it. So immediately we're already at 60. This has a minimum weight of 9. So it would be minus 18. That has a minimum weight of 2, which is minus 6. This has a weight of 4 attached to it, which means it could actually weigh exactly 9. And it would work out flawlessly. If we maximized absolutely everything, everything would line up perfectly. There's also an implied entropic line here. That's 789. That's besides the point, yeah. What if we minimized it? If we minimize this side. So I said, like, if this was maximal, then, yeah, so it's possible that's maximal. And we actually have a lot of room to work around with. Which is a little frustrating. Actually, no, we don't have any room to work around with if that's a 9. Because didn't I just minimize these, or did I accidentally maximize them? Minimum of 9, so it's 18. Minus minimum of 2 is minus 6, 36. Okay, yeah. So I said that these were a minimum in order to try letting this have the maximum possible weight. And if that's a 9, these are a minimum, these are a maximum. Now, I assume if I lower that number, different things will happen. What is the minimum weight that this could possibly be? Well, it could be 1. So it'd be 4 plus maximum weight that could be. Well, if that's a 1, then this would also have to be a 1. Or that could be a 2. That'd be 6. Sorry. Had to be 9. Yeah, this would be, if this is the minimum of 1, which I'll just put here. This is a minimum of 1, means that this is not a low number. Means that this is a middle number, which means that's a low number, which means the biggest it could possibly be is 3. So we have 17 times 2 plus 9 plus 4. If this is a 1, then this maximally comes up to 19. Can we minimize this side to be less than 50? Well, this is a minimum of 7. This can be as low as 3. So this is as low as 30. And that's 9. So yeah, we can. We can easily minimize that lower. That's frustrating. We got a significantly big, very, very large range to work with here. A somewhat frustratingly large range, honestly. Where is there progress to make? Ah, entropic lines. I think I've made a little bit of a discovery here. Ones can't go in either of those rows. This cannot be a 1. Yes, it can, can't it? That could absolutely be a 1. That's annoying, actually. I thought that was like, oh, you can't have a 1 there, so it has to go there. But no, you could have a 1 in either of those places. Well, that's red. Actually, interesting derivation. All the reds in this column are gone. These can't be red. We need to have 2 more reds in this area. Only one can be here. That has to be a red. Which is a really interesting line of logic, actually. I kind of like that. One of them must be red. One of them must be yellow. That's a yellow. I'm actually going to use green to indicate that right now because I haven't quite codified in yellow and blue yet. We don't quite know what those are either, but one of them must be... actually, could I do anything weird with that? Where those two have to be the same? Nope, I don't see anything obvious. That's the... Okay. This cannot contain any reds. That's orange. This has to contain exactly 1 orange. This contains none. How do you put the oranges in this column? 1, 0. These must both be orange. That's the only way to be able to fill up that column properly. The way to think about it is that there must be 9 oranges in all of these columns. 6 in those. And there must be in groups of 3. Okay. So, in this column, we've 5 to go. Yep, so now grand total we have 5 to go. This is done here. These can't be here, so we have 4 to go. Still 4 to go. And we can only have, 2 to put here and 2 to put here. These both have to go there. None can be put here. We still have to put 3 in this column. Both those must go there. Okay. Interesting, which means that's... Well, one of everything is here. We have a middle and a low here. All of those are covered for us. This is either a middle or a high, because we have this as the opposite. So it's either a green or a red, whatever the opposite of that is. Wait a second. Red's in this column. Could be these, but blues in this column. This or greens in this column. Yeah, so these are the only places where we could have reds. Ah, there we go. That's a middle. That's okay, so we have to swap these around. So these are... We're just going to do this for now to interim them. These are mediums because they can't be smalls because there's 3 smalls here. Can't be large because the larges are there. So it must be mediums. Mediums are yellows, so I must remove these, which I will replace those with greens as being the in-betweens. There we go. Okay. We're going to use yellows as our middle numbers. And usually I use blue to mean small. There we go. Okay, that's better, that's better, that's better. These are blue. Okay. Whew. Makes me feel a lot better, honestly. I don't like the coloring scheme typically, so oops. There we go. Okay. Whew. That makes me feel a lot more relaxed, honestly. So that has to be, well, we may as well fill them in. 4, 5, 6. 1, 2, 3. Which means, well, this still can't be 6. Whatever, it's not a huge deal. But this is going to be the opposite of whatever this is. Because now we have both those covered. These are going to be one of each. This has to be a... I effed up. That shouldn't be like that. This is blue. This has to have one high, one middle. Okay, cool. That makes sense. That maths out. Because there is one blue here, one blue here. And that adds up everything because there's another blue right up there. Okay. 1, 2, 3. This can't be a 4, 5, which means this can't be a 1, 2. Well, this is reasonably small. Can this be small? Is this possible to be a blue? So if we maximize this, maximize that to be a 3, maximize that to be a blue. Then we have 9 plus 1 times 4, which is 4 plus 17 times 2 is 34. So this equals 47 torque if we have this as a 1. What could this be? As a minimum, we have 7 plus 6 times 3 plus 9. 48 as a minimum. This can't be a 1. Yeah, so that can't be a 1. This can be lots of other things, but it cannot be a 1. Deduction has been accomplished. This can't be a 1, that can't be a 1. Whew. Lots of other values to start taken away, little by little. Can it be a 9? Has this somehow shrunk our opportunity size a little bit? 9 plus 8 is still doable, so it's 17 times 3 plus 9 is 60. 4 times 9 is 36. So this could be less than 60, but it's at most 60. Actually, are we dealing with a multiple question here? Something about even odd parity? This, no matter what, is a multiple of 3. This is a multiple of 3. This torque must be a multiple of 3. That must be a multiple of 3, so that can be ignored. 4 times this, or just that, and double that, must equal a multiple of 3. If that's 4, 5, then this has to be a multiple of 3. If that's, oh no, if it's 4, 5, yeah, if that's 4, 5, it has to be a multiple of 3. If that's 8, 9, 17 times 2 is 34, so this has to be a 2 mod 3. Interesting. So the results of these numerically affect what that's allowed to be. That's really cool. Yeah. All of the blues are here. These both have to be yellows. One of these is a yellow, one of them is a red. Makes sense. Okay. Oh, I love these puzzles so much. I love entropic lines. I don't know why, but I just absolutely soak them up. Now we know that this can't be red, and that if these guys aren't red, this has to be blue. That's all that we know. If these guys are red, we have gained no information. But if these guys are yellow, then that's a blue. Is that impossible somehow? I don't think so. I don't think we have enough given information to deduce that. This must have one of each. This must have one of each. This must have one of each. Well, this is one of red, yellow. That's one of red, yellow. That's one of blue, red. Yeah, it has to be blue, red. Red, yellow. Red, yellow. Red, blue. I can actually codify that, can't I? Red, yellow. Red, yellow. Red, yellow. Sorry, that's not red, yellow. That's red, blue. Those are the possible colors I have working with me. This is yellow. That's yellow. That's red. That's red. Ah, here we go. Now we have those both be yellow. In this case, these are the exact same. If they're both yellow, we have a contradiction. So they can't both be yellow. Which means that has to be yellow. Cute little deduction here. That's a yellow. I don't see any obvious continuations of that logic, unfortunately, but yeah, it's something. This is its own beast, which we haven't even come close to thinking about yet, but I'm still not going to bother. I don't think that's something I can actually think about quite yet, because it's just another random balancing board. If this is not a multiple of 3, there's like then we can uniquely identify it based on this, that they have the same. Ah, those two cells and that cell have to have the same base 3 parity, or the mod 3 parity. Here's why. This has a multiple of 3, that's a multiple of 3, which means that entire balance is a multiple of 3. Here's the thing about modulus. If this is a mod 3, if this is a mod 3, that must be a mod 3. Because then they all mod 3 out. On the other hand, if this is 1 mod 3, then it contributes a 2. This then needs to be 1 mod 3. So 1 mod 3 means a 1 mod 3. If this is 2 mod 3, then it contributes a 1 mod 3. And then this needs to be a 2 mod 3. So 2 mod 3, 2 mod 3. So this has the same modularity. That's really interesting, actually. So we know it can't. So if this was 6, yeah, if this was 4, 5. Yeah, so we can actually reduce. So we can't figure out what color it is. We can figure out which third of the entropic colors we're working with. That's so fucky. Uh-huh. Wouldn't it be really interesting if I could somehow show, like, how the grouping worked too? Yeah. So if this is 9, then this could be 4, 5. But if it's 1, this can't be 8, 9. That has to be 7, 9. If that's a 1, that has to be 7, 9. So actually, yeah. Okay, so let's try this again, where we maximize everything except for this, and see whether that can ever be a 1. What's the minimum of the left side? Let's reevaluate that once again. 2 plus 4 is 6, plus 7 is 13. This weighs 13 times 3 is 39, plus 9 is 48. This side mandatorily weighs 48. This we established is going to be minus 4, being a 1. Then we are going to maximize everything else and hope that we can get this maximum over that. So, minus 9. The maximum this could end up being is 9 plus 7 because of that parity thing. Because 9 plus 8 would have it would be excessive, but we can't actually get it to... Oh, no, yeah, because... Yeah, there is no way that can ever be 9 plus 8 and be balanced. Just by the definition we showed before, it has to be 9 plus 7 in order for it to be a theoretically possible balancing act, which is 16. 16 times 2 is 32. It's not sufficient. That can't be a 1. Can it be a 2? If it's a 2, then we have access to, well, still the same thing, 3 here. We do have access to 8, 9. But if it's a 3... Can this be a 3? This then needs to be 7, 8 maximally. Because that's the highest possible multiple of 3 that we have. 15 times 2 plus 6 plus 12, 51, which gets over the 48 value. Jeez. But only barely. With 3 and maximizing everything else. Well, if that's a 3, then we already have that, but that's fine. But it's those. We only barely squeeze by. Because we have 48 on the other side. Can we increase this value by 1? We can. No, we can't. We can't increase it by 1. Because that's 7, 6 minimally. We'd have to either increase this by 1, which we can't, or increase this by 1, which we can't, because then it'd be even, which means this can't be a 3. We have this being a 2, 7, 8, 9. And we now showed the same thing with 7, 8, and 9. I love this puzzle. I really hope this is the intended pathway. Okay, so now we're going to minimize this side, with this being big numbers, and we're going to maximize this size and see whether we can get there. So we have 9 plus 8 is 17 times 3 plus 9. Left side maximally creates 60. 9. So what we need to do is we need to be under 60. Actually, 9 is probably doable because we can have 4 and 5. 8 is where things get weird. 8 times 4 plus 6, where we have 2 times 3 is 38. We need to get below 60, which means we have 22 to work with. Which means these need to be 11 or less. It can't be 11 or less. Because here, since this is 8, this needs to be 2 mod 3. And needs to be on the same line, which means it needs to be 9, 8. That's the only option we have, which breaks. That can't be an 8. Can it be a 7? Oh man, that gets spicy. So again, we have 60 maximum level if we have to stay below it. 7 times 4 creates 28 plus 6 minimally. 34. We have 26 to work with, which means this has to be 13 or less, which it cannot be. This can't be a 7 either. That's a 2 or a 9. Sweet, which means we never have 1 mod X. Which means we never have a 7, 9 here. They're always adjacent numbers. They're either 4, 5, in which case that's a 9. And then we can actually get specific values now. Okay, so wait. 9 times 2. So yeah, we're going to see whether it's possible to make the left side equal exactly using a 4, 5 pair. So we have 18. If this is a 4, 5, then that has to be a 9. So 18 plus 4 times 9, 36. And now we either have plus 6 or plus 9. So we have either 60 or 63. We can reach exactly 60. By maximizing everything here, we get exactly 60. So if this is a 4, 5, it is a valid combination. 7, 9, and 2 would also be a valid combination, I believe, as we showed before. Sorry, 8, 9, 2 is what I mean. 7, 9 isn't doable. That has to be a 2 or a 9. Cool. That was really cool logic. I really hope that that's correct and that I figured that out correctly and did the math on that right, because that is just mind-blowing if so. Well, this is also 4, 5, 6, 7, 8, 9. Can't be an 8. This would then also be a yellow. Let's just finish up the rest of the line here that we have. Well, we know these can't be blue, which is fine. So I guess I could technically write this as yellow-red split. Well, this is also yellow-red split. Whoops. That's also yellow-red split. But only one of those is yellow. Interesting. That's a 9. Then that can either be 7, 8 or 4, 5. This has to be 1, 3. Yeah, 1, 2. One of those has to be a 1, which you just know because there's no more 1s in there. This can't be a 2. That's yellow-red only. These can't be blue. Those are the only places that could be blue. That's blue-red. It's also blue-red, isn't it? Because it can't be yellow. Yeah. So then we have to have one of these be a red. Well, if that's red, then that has to be the red. And that's a blue. I don't see any issue with that. So one of these three cells is red. No, it was blue, sorry. The other two are red. Can these both be red? That's what we're going to consider now. Those are both red. Those are both blue. Let's bifurcate a little bit. Those are both red. Those are both blue. This is then red. That's blue. That's red. Just the way that this logic all works out. That means that both of these are yellow. There needs to be another yellow in here, which means neither of these can be yellow or blue. They'll both have to be red. Which means that can't be a red because that's a yellow. One of those is yellow, one of those is blue. One of those is yellow, one of them is red. That can't be a yellow, so it's gonna be a red. That's gonna be like that. I don't see any issue with this. This have to be a 3, 2, 1, 3, 2. Yep, I see no issue with any of that. There's no obvious issues with that, so I'm not gonna bifurcate further. I was just bifurcating the coloring. I'm not gonna go like much beyond that. Bifurcate the coloring and what are the obvious natural conclusions from it. It's kind of unfair to go much beyond that. Hmm. Uh, if it's this has to be a 3. If it's this has to be a 3, this has to be a 2, this has to be a 1. No matter what, there has to be a 3 here. Right. Because that can't be a 3. Neither can be a 3. Which means both of those, yes, which means no matter what, that's a 1, that's a 3. Which means that can't be a 3. Unfortunately, that creates a shifted triple here. Doesn't actually resolve anything. What the heck? It goes all reds. Oh my gosh, that's really cool. I didn't realize that highlights all blues and reds and all together. Anything that is blue or red. That's all the ones that are colored blue. That's all the ones that are colored red. That's all the ones that are colored blue and red, or blue or red rather, including the multis. I didn't know that that's how that worked. That's a really good highlighting function. Mm. Right. Don't see anything painfully obvious. Which makes me think that I might need to revisit. But I don't know. So we now know that these must have the same 3 parity. Do we know anything about the relationship that these guys have? So it can't be 7, 9. So it can't be. Is this always odd? 7, 8, or 8, 9, or 4, 5. It's always odd. This is 2 mod 4. Let's do mod 12. Yeah, let's work with mod 12 in my head for a moment. So this is. So yeah, let's just think of the possibilities. We have it equaling 9, which twice that is 18, which is 6. So we have a 6 mod 12, or we have 15 times 2 is 30. 30 mod 12 is 6 again, or we have 1734, which is a 10. So we have a 6 or a 10 mod 12. That's 10. So 6, 10. Which I'm just going to write that down very briefly just so I have them here. 6 or 10. Then the next area that we have a 2 or a 3 times 3. So we have a 6 or a 9. Nice. And then next we have a 2 or a 1. I think I'm just going to do a 2 or a 9. So 2 times 4 is 8. Or 9 times 4 is 36, which is a 0. Which means we have 660, 668, 690, 698, 1060, 10, 9, 10, 6, 8, 10, 9, 0, 10, 9, 8. Those are all the possibilities, which we have them now equaling. I could probably just like actually let me actually just manually calculate every fucking possibility. I think that's what I have to do at this moment. Calculate all the possibilities and see what I'm missing out on mathematically. We have. Yeah, the options are 9, 2, 9. That's the first possibility. We have 9, 3, 9. Then we have 15, 2, 9. And then 15, 3, 9. Which I'm going to do the adding afterwards. I'm just doing all the possibilities we start off with. And then we have 17, 2. No, it would be 17, 3, 2. And that's the only option we have for that. So 18 plus 6 is 24. 24 plus 36 is 60. So 929 gives 60. Then 939 is the exact same, but plus 3. So we get 63. We have 15 times 2 is 30. 36 and 36 makes 72. Same thing, but plus 3 gives us 75. 1732 is 34. Plus 9 is 43. Plus 8 is 51. So 1732. I've got to double check that math. If I have 8, 9, We have 8, 9 here. A 3 there and a 2 there. 8, 9 makes 17. That makes 34. 34 plus 9 gives us 43. 43 plus 8 is 51. Okay, so we have 75, 72, 63, 60, 51. Those are our combinations that we can work with, and the only ones that will work. Now we can go to the left side and we can see how all of this weighs. We can now subtract 9 from each of these and see how they balance against the left side. So I've got, instead of 51, 60, 63, 72, 75, I can subtract those weights off of each of those, which is just 9. And then I get 42, 51, 54, 63, and 66. All of those are divisible by 3, so let's divide them out. Divided by 3 gives us 42 divided by 3 is 14. Then we get 17, and then I get 18, and 63 divided by 3 gives you 21, and 66 divided gives you 22. What can this maximally equal? 9 and 8, giving us 17. So we strike anyone that are bigger than that, which would be the bottom 3 values. You could only have 17. What's the lowest it could be? Can we give this equaling to 14? We can. It would have to be 9 and 5. Can we make it equal 14? I don't think we can, actually. So with a 7, that can't equal 7, period. That's a 9, that would equal 5. We can't do it. The only possibility is making it equal 17 with 9 and 8. That's the only possibility. Which means we're working with the sum, which means these equal 9. This is a 9, that's a 2. These have to equal 9, which makes that a 5 and a 4. And then this is the only way that they even out correctly. 17, 51, 60, 9, 18, 9 times 4, 36, 18, 54 plus 6 is 60. They line up. That's a 1. That's a 3. That's a 2. Holy shit. So those are both yellows. That's a red. That's a blue. So it has to be a 1, 2, 3. Means it has to be a 1 or a 3. Jesus Christ, that was a really cool solve. This has to be a red then, which means that has to be a blue, which means that has also be a 1, 3. Which means these are all reds and yellows. We must have at least one red here. At least one yellow here. That's a red. At least one red. We don't know about here, though. Okay. That's fine. Man, that's... I don't think that's bifurcating. I think that's just resolving all the possible options. I'm going to call that a W in my book. Yeah, so now where do I move from here? That's a 5. So that's a 4. That can't be a 4 now. It's a 5, 6, or red. 4 has to be here. Which means can't be there, which means must be here. Whoops, sorry. It's alright, doesn't have to be here. That's what I meant to do. Because we already have a 4 there. Oopsies. Well, we can't have a 4 there. That now has to be red. All those have to be red. Okay. So this has to be the same as this. They can't both be yellow. Could they both be red? Is there a world where this entire thing is weighted on reds? 7, 8, 9, 7, or 8. Yeah, it could be. Oh, wait, no. 7, 8, that can't be a 9. So if this was all reds, if this was all reds, never if this to weigh less. This had to be 7, 8. There's no way this would ever have to be able to weigh less. And since that's the same, with this being, if this was a blue, there's literally no way that this would weigh more than this without being a blue if both of these are red, which means they can't both be red. Which means they can't both be, and they can't both be yellow either, which means they must both be blue. I still don't know what that is, but I know that the use case of it being red is impossible, and the use case of it being blue is impossible in the condition of both those being red. And since they're the same on the line, they can't be yellow, can't both be red, therefore must both be blue. Cool. And then therefore that's yellow. That's a 4. Okay. I've almost entirely done I've done the main balancing weights. Now I've got to do this smaller subset balancing weight. But well, is there a world where that's blue? I don't think there is. I don't think it's possible for that to be no, wait, sorry. Can't be blue, of course. Has to be the same as that. Can't be 9. So this is a 7 and that's an 8. They have to have 3, 1. That's the only possibility. Bouncing the 1, 3 here, forcing that to be a 3. I mean, it's possible. And then forcing that to be blue. I mean, it would cause a small chain reaction, but I don't think it's actually impossible. Yeah, so that could also be 7, 8. Yeah, so 7, 8. It could also just be 8, 7, and then we have a whole other. Well, 8, 7, and this still would just be higher than that. That makes no real difference. That could still be 9, 8, though, as well. We don't actually have enough information to assert that for sure. This has to be yellow. Because, so, this is a 4, 5. Because I see it's a 6. So that is one of a 4, 5. One of the other 4, 5 can't be there. So it has to be there. Which we already knew this here, but now it also can't be a 6. What are those? That's our red. Red, yellow. Yeah, it's 6 and 6, 7, 8. Cool. Means all the yellows are taken care of here. So we only have blue and reds left to work with down here. So this can't be a yellow. And then where do yellows go in this row? Have to go there. They have no other choice. Which means one of these has to be a blue, so that has to be a red. One of those is red, one of those is blue. I don't have enough information to assess either. Could see the same thing with red, blue there. And then we have the same thing with red, blue there. Two of these must be red, two of those must be blue. Don't know which ones. But you know they all have to be offset. Whichever one the red is there has to be the blue in the other. Yeah, we have equal amount, so we don't have a lot of information to work off of. Thing down here, oh, nope, could be red or blue. Well, we know that there must be one red and one blue there, which means this has to be blue. Because there has to be one red and one blue here, that makes the third blue here. Which means that's not blue. Which means that's not red. That's a 1. We're slowly trimming them away, little by little by little. We're slowly shaving away. Which means one of those is a 2. Well, now that we have this, one of those is a red and yellow. Red, red. We need this to be a red. Now we have equal blue-red parity here. Or each of those could be a blue or a red, and we don't know. But only one of these is a red. We have a maximum red capacity here, which is here we're looking at. Well, at least one of these has to be a yellow. Could we have 2 of these be a yellow? We could. I was doing coloring without even looking at the without the lines right now, because I'm not even considering the impact of those lines because I don't need to. Because I'm pretty much done with fusing them in terms of actual value I've obtained from them. This is the only line that I haven't completely solved yet in terms of actual like high, medium, low parity. Wait. That can't be a blue. And we're stuffed up on reds here. Because that's a red something pair. That's a red something pair. Means there must be one red here. Must be one red here. That means that of those, we are stuffed up on reds. And both of those be reds. Yes, they actually can be, can't it? Fudge. I thought that those can both be reds. But they can be. So that could still be a red. Well, that has to be a red-yellow. No matter what, this has to be red-yellow. We can't have any reds here. That's got to be yellow-blue. That's a red-yellow. That's a red-yellow. There must be a 2 here. There must be a 3 here. So one of those is blue, one of those is that. We have a yellow and a yellow. Yellow, yellow, yellow. So this has to be a red and a blue. That has to be a yellow and a blue. Do I just start picking out numbers for these? Before 6. That can't, oh, these can't be 5s. That's, I mean, a little. One of those has to be 5s. But we could put 4 anywhere there and it would be fine. We put 4 here. Then that's a 5. That's a 6. That's a 5. No problem. 4 here. That's a 5. Yeah, if we put 4 here. No, so if that's a 4, that's a 5. That's a 4. Put a 4 here. That's a 4. 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 Well, all those could be 4s. If that's a 4, that's a 4. That's a 4. That's a 4th, and that's a 4. One of those is a 4. One of those is a 4. One of those is a 4. That has to be a 4. I mean, I could do that bifurcation. Those are the only 2 possibilities. So there's one case where that's the 4. 1, 2, 3, 4, 5, 6, 7, 8. We have a case where this is the 4. Ah. This box. Those are all the places for 4. If this is a 4, then 4 has to go in one of those. These 4 has to go there. But then both of those cancel the 4 area there. That can't be a 4. That's a 6. That's a 4. That's the only way that maths out. Which means, there we go. That is the number we're looking for. That is, whoops, like that. Sweet. resolution. That's all the fours placed. Oh, that's still 5, 6 ambiguous, though. I know, that's be a 5. So that's a 6, that's a 5. Yeah. That's a 5. I probably missed some other stupidly easy way of doing that, but... What other 6s do I have? What a lot of 6s. Oh, crap. Well, that can't be a 6. We need a 6 to be whatever the last digit is here, so that's a 6. That can't be a red. That can't be a yellow. Which means we've got the 3 reds we need here. That's not a red. And now we don't have the 3 reds we need here, so that can't be a blue. Now we've got all the yellows we need. All the blues we need. Okay. Little by little, it's beginning to collapse. We got all the blues we need. We got all the reds we need. These are all vertical pairings. So until we actually place those digits, we won't know. But that's a 5. One of this has to be a 6. That's a 3-6 pair. Which means that has to be a 5. That's a 2, that's a 5. Which means that's not a blue, that's not a yellow. Which means that's a 2. If I trust my prior coloring, which I do. That can't be a 9, which means that needs to be a 9, because that's the only thing that could possibly be a 9, since that can't be, since that 9 there, that 9 there. That's a 7. That can't be a 7. That's 8, 9. That's 7, 8. Oh, come on. Just fall apart. Just fall apart. Come on. You're so close. So close. Teetering on the edge. Well, this one was a 3 to pair with those. That's 8 or 9. That's 8 or 9. That has to be a 7. That has to be an 8. That has to be a 7. That has to be a 7. 8. I'm guessing this is probably going to end up resolving the rest of the puzzle. Oh, come on. That's great. I just see that as being 8 or 9. I don't quite see that resolving yet. Is this actually not quite resolved? Do I actually have to figure out this here? That can't be a 9, so it's got to be 7, 8. If they're both 8, this has to be more than that. Which can be done in a variety of ways. Well, that's a 2. That's a 1, 3. One of those has to be a 2. That's a 2, that's a 2. That's a 1, 3. If that's a 1 and that's a 3, there is no way to offset that properly. because these could only have an offset of maximally 2, even if they weren't offset that way. So that's to be a 1 and a 3, which means, unfortunately, we've gained no information about those specific cells, except that that's a 3, that's a 1. Which means that's a 3, that's a 6. Which means that's not a blue, that's not a yellow, that's not a blue, that's not a red, that's not a yellow, that's not a red. Which means that's 6. Which means that's 1. That's 7, 8. Oh, that's 8. That's 8, 9. So that's an 8. That's a 9. That's a 7. That's an 8. That's a 7. That's a 7. That's an 8. That's a 9. Geez, so now if that's 12. Oh, whoops, I did this backwards. Whoopsie doodle. You didn't see that? This is supposed to be a 3, then a 1. Oops. Teehee. You did not see that. That was an advanced bifurcation method. That's all that was. Nothing else, I swear. That's can't be a yellow, which that can't be a red, which means, whoops, wait a second, that can't be a yellow, which means this can't be a yellow, which means that can't be a red, which means that can't be a red, which means that can't be a blue. Here we go. Oh, well, sorry, which means that can't be a blue, which means that can be red. That's a 1. Okay. That's also going to be a 7, 8. That's a 9. That's an 8. It's a 7. That's a 6. That's a 9. Which means that's 10. This needs to weigh more than 10. That has to be an 8. That's the intended resolution. 7, 9, 7, 9, 8, 9, 7, 8, 8, 9, 7, 8. Three, 1. Oh my god. That is a hefty, and incredibly fun puzzle. I had a lot of errors that I had to go back and fix. Oh, jeez. But hey, one take.